we are back with Solutions 102. This is the second part of Solutions 102. And what I'm talking about today are the three types of reactions or three types of equations that we can represent a double replacement reaction with. So, and your assignment, of course, is just to finish the AP Solutions 2 worksheet. And we know that we can represent a double replacement reaction with three different types of reactions. So three different types of equations to represent double replacement reactions. So we have molecular, complete ionic, and net ionic. Okay, and they're all related to each other. We're going to start with the molecular and move on to the complete ionic and the net ionic. So with a molecular equation, everything is shown as a molecule. Okay, so there's no charges shown. All of the ions are shown together. Even if they're aqueous, you still show them together. So we're going to do an example here, and we'll start with some lead 2 nitrate, and that's aqueous. So this would be our AB, and we will add to that, what should we do? How about some potassium iodide? And again, that's aqueous. Even though it's aqueous, we're showing it together because it's a molecular equation. And this would be our CD. So when we put these together, we are going to put together our lead and our iodide and our potassium and our nitrate. So over here, we would get PbI2, and based on our solubility rules, we would choose that to be the solid. And then in addition, we would get potassium nitrate, aqueous. Okay, so that's an equation. Now we have to balance it. So we want to notice that there are 2 nitrates here and 1 here. And so we're going to put a 2 in front of the potassium nitrate. And then we'll also put a 2 in front of the potassium iodide to balance the iodines out, and the potassiums too. So molecular equation, everything is shown as a molecule. There's no charges shown on anything, okay? So in general, we would do this, we would represent it like AB plus CD aqueous, and then we'd show AD plus CB. And one of these would be aqueous and one of them would be a solid, depending on which one is insoluble. So in these, we would choose, of course, our insoluble is the solid, and the soluble one is aqueous. And remember that your solubility rules on page 118 in your textbook, and you can easily look those up, or I can give them to you as well for you to remember those. Okay, so that's a molecular equation. Molecular equation affects also the complete ionic equation. You'll also hear this called the total ionic equation. And in a total ionic equation, all substances are shown as ions that are aqueous, and if it's a solid, then it's shown as a molecule. So you really have to hone in on the substance that is the precipitate, because that's the only one that you're going to keep together in this particular situation for the complete ionic or the total ionic equation. Okay. Whoop. I forget that that goes behind my head. Okay, so what I'm going to do is bring this equation right here. I'm just going to interpret this equation, and I'm going to bring it down and write the total ionic equation for it. So this is going to show lead, Pb, and then we show the charge, +2, and that's going to be aqueous. That's the beginning part of this formula here. And then we have 2 nitrates. So we're going to have 2 in front. We want to remember that a subscript on a polyatomic ion or on a monatomic ion then becomes a coefficient. And if there's already a coefficient in front of it, then you multiply them. Okay, and then the potassium is going to be 2 potassiums. And then the 2 gets distributed to the iodide as well, so we get 2 iodides. And that takes us halfway through the equation. All we did was break each one into their aqueous ions and showing them as aqueous ions. And then we have our next substance is the product lead to iodide. And that substance is a solid, so we keep that together as a molecule and show it that way. And then we would show our 2 potassiums, aqueous, and our 2 nitrates, aqueous, just like that. So you can see that the total ionic equation is quite a bit longer than a molecular equation to write. So that takes a little bit longer. Okay, so that's a complete ionic equation. And what we want to identify here are something called spectator ions. And these are the ions that do not make the precipitate. They stay the same from the reactants to the product side. Okay, so you're talking about stay the same in terms of charge and state of matter. So if the charge changes or the state of matter changes, then it is not a spectator ion. Okay, so in this case, we want to be able to identify our spectator ions, and so we would notice that nitrate, NO3, is aqueous, and there's 2 of them on each side, and the charge didn't change. So we know that nitrate is a spectator ion. And then potassium is the same way. Potassium didn't change. So we would identify potassium as a spectator ion as well. So it's important to identify your spectator ions before you go on to the last type of equation, and that is the net ionic equation. So I'm going to bring this down here. And we'll just talk really briefly about what a net ionic equation does. In a net ionic equation, we show only the substances that made the precipitate. Okay, so we don't show the spectator ions. Okay, so this is kind of like algebra in the fact that we're canceling across the arrow. We canceled 2 nitrates and we canceled 2 potassiums, and all we're left with up here is the lead and the iodide. So what we would do is just bring down what's left over that we haven't canceled, just like in math. So we have Pb plus 2 iodides makes PbI2 solid. So that's an example of a net ionic equation based on the equations that we just did. So remember, whatever substance it is that made the precipitate is what's going to be shown in your in your net ionic equation.